Hi everyone, my name is Jack and I'm the event supervisor for the Astrophysics event. I am currently studying at UCSD, majoring in engineering physics. This is the first of many videos that I will be making in order to guide you in your studying for this event. The plan for today is to first give a brief introduction of the event. Then we will begin talking about some basics of astrophysics. This event consists of three main parts: stellar evolution, extragalactic astronomy, and cosmology. In stellar evolution, you'll be learning about stars and the stages of stellar evolution. So, for example, what the difference between a neutron star, a white dwarf, and a brown dwarf is, or when a supernova occurs. In extragalactic astronomy, we will talk about things like the type of galaxies in the universe and a bit about dark matter. Lastly, cosmology is about the origin and evolution of the universe. Therefore, we will discuss ideas such as the expansion of the universe, Hubble's law, and the Friedmann equations. The math expectation is up to Calculus 1, which means that there will not be any math more advanced than that. But don't worry, most of the time you likely won't even need to know any calculus at all. Let's begin by first defining what a star exactly is. A star is a luminous body that is made up of gas. Luminosity just means how much energy a star radiates. A star creates and emits energy through a process called nuclear fission. Stars differ in mass, age, and composition. And from this, we can determine their other basic qualities, such as temperature, luminosity, and radius. Stars are often one of the most captivating parts of a night sky. I'm sure in the background, you can see a sea of stars, but how many are there exactly? It's estimated that there are 10 to the 21st to 10 to the 24th amount of stars in the universe. To give you some perspective, there are only around 10 to the 19 grains of sand in the world. A commonly known star that is located in the solar system would be our sun. One way to classify stars is by their color and temperature. The spectral types are represented by capital letters O, B, A, F, G, K, M. A common mnemonic to memorize the order of this is O, be a fine guy/girl, kiss me. Since this mnemonic was created, there have been some modifications. Three additional categories are also in the scheme: R, N, and S types, which turned it into O, B, A, F, G, K, M, R, N, S. The corresponding mnemonic would be, oh, be a fine guy/girl. Kiss me right now, sweetheart. Then a class L was introduced, so I'm not sure what the updated mnemonic is now. Of course, you can make up your own if you're not a fan of this one. For the purposes of today, knowing O, B, A, F, G, K, M will be sufficient. Anyways, O would be the hottest spectral type. Then the rest is in descending order, with M being the coolest spectral type. As you can see from the chart, each spectral type differs in color, with O being blue and M being red. This might be counterintuitive for some of you, since in our typical lives, red usually signals hot and blue usually signals cold. But when we're talking about stars, remember, blue is hot and red is cold. In addition, each of the spectral types can be divided up into 10 spectral classes, numbered from 0 to 9, with 0 being the hottest and 9 being the coolest. So a B5 star would be a light blue hot star that is hotter than a B7 star. And both of these would be hotter than an A0 star, which would be like a white kind of hot star. We will be using this information shortly on the next slide. In the early 20th century, two astronomers, Hertzsprung and Russell, independently found a way to plot all the stars in the universe. This eventually became known as the Hertzsprung-Russell diagram, named after the two scientists, or HR diagram for short, which is what you see here on the right. This is one of, if not the most important diagram you will encounter in astrophysics. If you take a look at the axis, you'll see that how high or low you are on the chart depends on the luminosity compared to the sun, or the absolute magnitude. The luminosity is measured using a logarithmic scale. What that means is basically every tick mark on this vertical axis has 10 times the luminosity of the previous tick mark. So if a star is located at this place in the diagram, it will be 10 times as luminous as the stars that are located in this area, and so on and so on. And where a star is located on the horizontal axis depends on its effective temperature or spectral class, which is what we just talked about. One thing to pay close attention to here is that usually as you move to the right, the temperature goes up. But on the HR diagram, it's the opposite. By convention, the left side shows the hottest temperatures. And as you move to the right, it gets cooler and cooler. You see this reflected in the spectral types at the bottom as well. In other words, the top right corner shows the cool and luminous stars. The bottom left corner shows the hot and dim stars, and so on. Take a minute to think about where the hot and luminous stars would be located. Back to the astronomers. When they plotted all of the stars on this diagram, they saw that it created a pattern or clusters of stars on the diagram. They found that most of the stars were found in a band from the top left to the bottom right corner. This is known as the main sequence. And this is where the stars, in fact, about 90% of the stars are in the main sequence. And this is where the stars spend the majority of their lifetime. Above the main sequence, that's where the supergiants and giants are found. As suggested by their name, these stars are very large and luminous, but relatively cool. Below the main sequence are the white dwarfs. These are small in comparison and aren't very luminous, but they are very hot. Let's try to find where the sun is. Since the luminosity is compared to the sun, then we know that the sun should be where this one is. Then, for the horizontal axis, we can use our knowledge of its color. If we go back to the spectral type chart, we can see that the sun probably has a spectral type of G, knowing that the sun is a yellowy orange color. Let's check that. So 1 and then G. So yeah, we were right. That does lead us to the sun. So hopefully that gave you a better idea of how this chart works. Before we end for today, I just wanted to share with you some recommended resources. There are numerous really good introductory astrophysics textbooks out there that I recommend you to check out when you're studying. You can use them to follow along with what I'm talking about in these videos and also to dive deeper into each of these topics. I just listed a few here, but I'm sure other textbooks that you can find are equally as wonderful. Also, if you feel comfortable with this information, feel free to take a look at some more advanced books as well. I think you'd find them insightful. Similar to textbooks, there are a multitude of helpful websites such as the two I listed here that can assist you in your learning. In terms of software, I personally used Stellarium before, and I find it to be very nice if I want to study the sky and stars. I think it will be useful to you when studying any astronomy-related fields in general. Finally, if you would like to contact me for any reason, the best way to do so would be by emailing me. My email is shown here at the bottom. And that's all for today. We will continue talking about stellar evolution in the next video, and I'm looking forward to seeing you in the next one. Have a stellar rest of your day.